Welcome to today's Explainer. I'm your host, and today we're going on an incredible journey. We're going to start with a deceptively simple childhood question and use it to unravel the grand mathematical mechanics that govern our entire universe. We'll explore the forces holding planets in place, the incredibly delicate lab experiments that prove they exist, and how this whole magnificent cosmic dance actually works.
Okay, let's dive into this. Why doesn't the moon fall to Earth? You know, it's a brilliant question that pops up all the time on internet forums. It almost sounds naive, right? We're so used to the moon just hanging out up there in the sky. But if Earth's gravity is constantly pulling on it, exactly like it pulls on an apple falling from a tree, why doesn't the moon crash right down on our heads? It's a simple question, but it totally challenges our fundamental assumptions about how the world works.
Here's our roadmap for today. First, we'll look at the mystery of the falling moon. Second, the laws of gravitation and energy. Third, the extreme measurement precision of the Cavendish experiment. Fourth, the mathematics of damped oscillations. And fifth, we'll wrap up with orbit, gravity versus inertia. Let's start with part one, the mystery of the falling moon and how to miss the Earth entirely. To answer our main question, we have to accept a startling, totally paradoxical truth. The moon is, in fact, constantly falling toward Earth. Every single second, gravity is pulling it down. But there's a catch. It just keeps missing. There's a standout quote from our sources that perfectly captures this. That's the whole point of an orbit, moving so fast perpendicular to the fall that you never reach the center. And man, that is the absolute magic of orbital mechanics. The moon is moving sideways so incredibly fast that while it falls downward, the curved surface of the Earth literally just curves away from right underneath it. Moving on to part two, the laws of gravitation and energy and Newton's core principles. To really understand this cosmic miss, we need to establish the foundational rules of our universe. How exactly does gravity interact with objects, and what does energy have to do with it? Well, the crucial point is Newton's law of universal gravitation. It tells us that the attractive force between two bodies depends on their masses, and it drops off really quickly as they move apart, inversely proportional to the square of the distance, to be exact. But we also have to look at mechanical work and energy. Work is just the process of a force changing the energy of a system. But for the moon and its circular orbit, the pull of gravity is perfectly perpendicular to its sideways motion. And because of that, gravity actually does zero work. The moon's kinetic energy, the energy of its motion, stays perfectly constant, while its potential energy, based on its position, sits in this absolute perfect balance. And get this, all of these gravitational interactions across the whole universe, from a falling apple to swirling galaxies, are governed by one unbelievably tiny number, the universal gravitational constant, or g. It's 6.67 times 10 to the negative 11th power. That number is so vanishingly small that gravity is actually, by far, the weakest of all the fundamental forces of nature. Which brings us to part three, the Cavendish experiment and extreme measurement precision. If this force of gravity is so incredibly weak, how on earth did physicists ever manage to measure it? Welcome to the laboratory. We're looking at a modern, computerized Cavendish balance. Now, what's really interesting here is the heart of this apparatus. It's a tiny pendulum suspended by a delicate tungsten wire that's only 20 microns thick, barely visible. Inside the box, you have small lead balls, and outside, large lead balls. The microscopic gravitational pull between the large and small balls actually causes this unbelievably thin wire to twist. The sensitivity is just absolutely astounding. Some university setups can measure forces down to a single piconewton. Now, measuring such microscopic forces demands insanely strict laboratory procedures. But these aren't just dry, boring tasks. They're really thrilling obstacles the scientist has to overcome to unlock universal gravitation. You have to perfectly level the platform in two directions. You've got to rigorously calibrate angular displacements down to a fraction of a milliradian, plus or minus 70.0 milliradians to be precise. And whatever you do, do not break that brittle 20-micron tungsten wire. Literally, the slightest vibration from footsteps in the hallway outside can completely obliterate hours of collected data. It's the ultimate test of patience and extreme mathematical precision.
Let's look at part four, the mathematics of damped oscillations.
The moment those spheres on the Cavendish balance start interacting, the wire resists the twist, which creates torsional oscillations. Because there's resistance in the system, we can see in the data that the movements map perfectly onto a curve of damped harmonic motion. But here's the tricky part.
To accurately calculate the universal gravitational constant, g, your data has to fit that mathematical model flawlessly. For that to even happen, the initial swing amplitude has to be more than 8 to 10 milliradians from peak to trough. Any smaller, and the data just won't align with the math. Physicists actually use incredibly complex differential equations to account for that damping factor, calculate the period, and finally extract the exact value of g from this microscopic dance.
And finally, Part 5, Orbit, where we pit gravity against inertia.
Okay, armed with our incredibly precise understanding of gravity, let's leave the lab and head back out into space. To finally solve our falling moon mystery, Isaac Newton came up with one of the most elegant thought experiments ever. Imagine a giant cannon sitting on the peak of the tallest mountain on Earth. Let's move through this and see how it builds. Step 1. We fire a bullet or cannonball, horizontally. It travels a bit, then falls to Earth in a parabolic curve. Step 2. We use more gunpowder, a faster rifle. It travels much further before hitting the ground. Now, Step 3. Imagine firing it with such absurd, mind-bending speed that the cannonball flies forward so incredibly fast, the curved surface of the Earth drops away at the exact same rate the cannonball falls. Bingo, you are in orbit.
And this brilliantly illustrates the constant cosmic tug-of-war happening out there. On one side, you have gravity. It's pulling the object inward, mercilessly trying to drag the moon straight down to the center of our planet. But on the other side is the moon's colossal inertia. Thanks to its massive velocity and size, that inertia wants to pull the object away, carrying it off in an absolutely straight line into deep space.
I know, astrophysics can feel a little abstract. So let's bring it back down to Earth with some simple everyday analogies. Imagine grabbing a bucket of water and spinning it rapidly around yourself. The water doesn't spill out, right? Because inertia is pressing it against the bottom of the bucket, pulling it outward. Or think about tying a tennis ball to a string and swinging it fast in a circle. You can physically feel the ball trying to escape, pulling tightly on that string. That string? That's acting exactly like gravity. An orbit is just the delicate ongoing balance between those two massive forces.
Now, the speed required to keep this perfect balance depends entirely on distance. The further away you are, the weaker the gravity, so the slower you need to travel for that centrifugal effect to offset the fall. Take the International Space Station. It sits really close to Earth, which means it has to absolutely race at a blistering 8 kilometers per second just to stay up there. But the Moon, it's much further out, so it only needs to travel at a leisurely 1 kilometer per second to stay perfectly suspended.
We started our explainer today with a falling apple and a tiny tungsten wire. And we've ended up dissecting the mechanics of entire planets. But here's what's truly astonishing. This delicate, eternal balance of the cosmos, it isn't actually perfectly static. The moon is, millimeter by millimeter, moving in an expanding spiral, very slowly drifting away from Earth due to tidal forces. Which leaves us with a pretty fascinating thought. If the laws of physics are so strict and constant, how long will this particular cosmic dance last before the universe writes an entirely new chapter in its mechanical history? Keep exploring, keep asking those simple questions, and never stop wondering about the mechanics of our universe.